Um, Good afternoon, everybody. So we are here in the third tutorial of today's. Uh, this tutorial is from Walmart Global Tech India, and the topic is very interesting. It's on causal inference and causal machine learning with practical applications. The presenters are Somadeep, Somojit, and Dheeraj. And I would like to invite them to come to the stage and start the tutorial. Thank you very much. Clapping.
Thank you, Vipul. Good afternoon, everybody. Thanks for showing interest in this tutorial on causal inference and causal machine learning with practical applications. So let's start off the tutorial by asking a fundamental question. So what is causation? So we keep hearing this word. So causation, as per the dictionary definition, goes on to say that it's the action of causing something or it's a relationship between cause and effect. So we are involved with this in day-to-day activities even without our knowledge. So we are always curious as individuals and also as researchers to know what caused what. So what phenomenon caused what other phenomena. So what caused a dip in the stock price or what caused a change in the weather. So we have examples across domains. So did an ad campaign lead to an uplift in the sales in marketing? And in medical sciences, we want to understand the effect of drug on treatment. For example, if did a new treatment work better for cancer patients? And across domains, we have examples like this. So in causal inference terminology, so X is typically called as a treatment or an exposure or an intervention, so the thing which we want to uh, observe the effect on, and y is the outcome. So x is a treatment and y is the outcome. So all of these, across these examples, you can observe that x and y are associated with each other or correlated. So if x and y are associated with each other, can we say that x has a causal effect on y? Let's see an example. So this is an example where it shows the graph between the cheese consumption and the number of engineering doctorates awarded between the years 2000 and 2009. So, so clearly we can see that both of these are correlated. There's a very strong association. But can we say that consuming more cheese would give you a doctorate degree? No, right? Definitely not. So if correlation is not causation, then what is causation? So how can we say that one thing is causing the other, or how can we measure the effect of the cause on the effect? So we enter into the world of causal inference. So throughout the course of this tutorial, we would be talking of few concepts and terminologies, and what are counterfactuals, some matching techniques, RDDs, and so on. We'll also have a hands-on exercise. We'll also talk of the machine learning models that are available to extract the causal effect of treatment and outcome. Examples like uplift models, meta learners, and so on. We'll also have a hands-on here as well. So suppose, let's say you are having a headache, and you take a pill, you take a medicine for the headache, and you observe that your headache is gone after some time. Then how do you say that it is the pill that caused the headache to go away? So how can you say that the medicine that you took has a causal effect on the headache? So to understand this, we need to know what are potential outcomes. So here in this example, the treatment is taking a pill, and the outcome is whether the headache went away or not. So potential outcomes are the possible outcomes for each of the treatment levels. So the treatment levels here could be taking a pill or not taking a pill, and what could be the outcomes, the potential outcomes for each of these treatments. Suppose the treatment is taking a pill, the headache might go away after you take the medicine, and the headache might stay. So you don't know. So these both are the potential outcomes for the treatment of taking a pill. And for no treatment, also you have two potential outcomes, which is the headache might stay or the headache might go away. So how do we know if the pill has a causal effect on the headache? So we define the causal effect as the difference in potential outcomes. So if the potential outcomes differ from each other only, then we can say that there is a causal effect of the treatment. Suppose treatment is equal to 1, that is you take a pill. So the do operator here means that you're actually doing the treatment, or you're actually taking the pill. and you observe that the effect is 1, the outcome is 1, that is the headache has gone. And on the other side, you also don't take the pill, and you see that the outcome is 0, that is the headache stays. So we define the causal effect as the difference in potential outcomes of y1 and y0. So only if this difference y1 and y0 are different, then we can say that there is a causal effect of the treatment. uh, T is the treatment that is observed, can be 1 or 0. Y is the observed outcomes. I are individuals, so individual treatment units, and yi and y0 are potential outcomes. So the causal effect is the difference in potential outcomes. But you can see an obvious challenge here, right? Obvious problem. So that is, we can observe only one of these potential outcomes. So we cannot have treatment and no treatment at the same time, right? So this is also called the fundamental problem of causal inference. So we could know only one of the outcomes. We can either take the pill or not take the pill, right? So we cannot do both at the same time. So if we cannot do both at the same time, how can we even measure the effect? So suppose you take the pill, that is t is equal to 1, and you observe an outcome, that is y1 is 1. So which is the factual case. But there is a counterfactual case. So how do we know what could have been the effect if no pill was taken? That is, if t was 0, what would have been the effect? We don't know. So only when we know these effects, we can measure the causal effect. So the causal effect here is practically unknown, because we can observe only one of these numbers, one of the potential outcomes. It's also true in the other case. If the factual is t is 0 and the counterfactual, we cannot know the counterfactual at the same time. So again, we cannot measure the causal effect because we know only one of the measures. So what is the way out? What can we do about it? So we can look at an average treatment effect. So here we have been looking at one individual. So we can get around this by looking at the population of individuals. So instead of looking at y1 minus y0, which is the individual causal effect, we can look at the expectation of y1 minus y0 across a population. Suppose we have a population of individual, or a sample of individuals, 6 individuals, and they have different treatments, 0 or 1, and we can observe y1 or y0 for any one of the individuals. So if we want to look at the expectation of y1, so there are a few unknowns. So because we can only observe one of the potential outcomes, and similarly there are a few unknowns in y0. So how about we take a conditional expectation? So instead of looking at the difference in expectations, so we could look at the difference in conditional expectations. So if for the conditional expectation of y given t is equal to 1, we could calculate the expectation here, which is 2 by 3. And for t is equal to 0, that is no treatment case, it is 1 by 3. So the difference of this, the 1 by 3, we can say that it may be a causal effect. But if you can see, it's not always the case, because the difference in expectations is not equal to the difference in conditional expectations. So why? Because we have the effect of confounding. So there could be other variables or other factors that could be affecting the outcome, and the subpopulations that we are considering in the conditional expectations, for the subpopulation of t is equal to 1, the subpopulation, the individuals are 2, 3, and 6. And for the subpopulation t is equal to 0, the individuals are 1, 4, and 5. So these individuals or these subpopulations can be entirely different. So we cannot say that the difference in expectations is the difference in conditional expectations, because of the confounding effect. So what are confounders? So confounders are external variables which would affect both the treatment and the outcome. Going by an example, suppose the treatment is an independent variable which affects the dependent variable, the outcome. So there may be other factors or other variables called the confounders, which would disallow you to capture the direct treatment effect of the treatment, or the causal effect of the treatment, because they would apply, or they would act both on the treatment and the outcome. If we look at an example, so if we want to understand the effect or the causal effect of alcohol use on lung cancer, So if we want to know whether alcohol use is really causing lung cancer or what is the effect of it, so there may be an effect of confounding called smoking, which could affect both of them. So smoking might tend to uh, force you to uh, have an alcohol use, and smoking might also have an effect on lung cancer. So smoking is a confounder here. So let's look at an example with numbers. Suppose we want to understand the effect of obesity on CVD, cardiovascular disease. So in this example, there are 300 obese people and 700 non-obese. So if we look at the incidence of cardiovascular disease in the obese people, it's 46 over 300, which is 0.15. And the incidence in non-obese persons, it's 60 by 700, 0.08. So clearly we can see that cardiovascular disease has higher incidence in obese people. So, but this sample is across an age segment of 35 and 65. So there could be the effect of age, right? So age can affect both obesity and the incidence of cardiovascular disease. So if we look at the numbers, so we observe that age indeed has an effect on obesity. So older people have a higher incidence of obesity, which is almost 50%, but younger people less than 50 have it's only 16%. Similarly, age also has an effect on cardiovascular disease. So we can say that the effect that we are looking at is confounded by age. So how do we capture or how do we neutralize the effect of confounding? So randomized control trials, or they're also sometimes called A/B tests. So they are considered as gold standards in identifying causal effects. They are also very powerful in removing the effect of confounding. So in RCTs, so we start with the population of interest. So we want to give everyone the treatment and everyone no treatment, but that is not possible because of the fundamental problem. So we randomly split the population into two groups: world one, where everyone takes the pill in our example, or everyone takes the treatment, and in the second subpopulation, which is also randomly selected, so everyone does not take the pill. So then we measure the mean outcome or any other metric of interest in both the subpopulations. We can then look at the difference in the outcomes of the subpopulations. So since these subpopulations are randomly selected, so the only thing that could be different between these subsamples could be the treatment effect. So this will make it possible to equate the difference in expectations to the difference in conditional expectations. But it's not always easy. So to carry out RCTs, it's not always easy. So and RCTs are also experimental studies, but what about observational data? So this is one challenge, and on top of it, so they may be unfeasible. They may be very high cost experiments, and there are a lot of risks, and there may be ethical reasons. So you cannot force someone to smoke who is a non-smoker to study the effect of smoking. So we have ways to get around this for observational studies. So one is the instrumental variables, the instrument variables. So instrument variables are variables which affect only the treatment. They wouldn't affect the outcome. So the only effect of the variable on the outcome is through the treatment. So if the treatment is confounded by any other factor, so we can get to an instrument which we can use to estimate the effect of the treatment. So the treatment, so there are two main criteria for defining an instrument. So it causes variation in the treatment variable, and it does not have an effect on the outcome directly. So the only effect is through the treatment. For example, if you want to study the effect of years of education on wages, so ambition could be a confounder. So it might so education is not necessarily always factor to earn higher ages or lower ages, right? So ambition could be one confounder. So there could be some instrument variable which we can use to study the effect of years of education in its place, because it is confounded by ambition. So and it's This is one of the methods, and sometimes it's also not possible to find an instrument, and they may not even exist in some cases. There are other methods also to get around the effect of confounding, so which Shomajit would be taking you through. Invite Shomajit.
Hi. Um, Thanks, Dheeraj, for taking us through confounders. So now we move to something called matching. Now, why we'll look at matching and why it is important. Um, we talked about counterfactuals, right? So counterfactuals are what Dheeraj said is essentially control variables in observational studies. What that means is some some observations or the observational units that did not go through treatment. How do we find that? Right? Inherently, when we are comparing a treatment with a control, or in this case, counterfactual, the observation that we are comparing, at least in this case, let's say we are talking about people who are smokers and non-smokers, they inherently have to be same, right? Similar sort of people. We can't just compare apples to oranges in terms of how people are. Here it could be people, it could be something else somewhere else. You can think of COVID vaccines and anything for that matter. So matching, what it does is essentially it tries to find that equivalence, right? So in past data, we are all of, here we are talking about past data, and not anything else in this. So in the past data, uh, if we've given somebody has taken smoking as a habit, for example, we need to find somebody who is very similar but who are a non-smoker, right? For us to compare the impact of smoking, cancer, etc., etc. So the work of matching comes here. So it sort of the threefold, right? First is experimental methods, which Dheeraj was alluding to, such as A/B testing. It does consider randomization, but it could be randomly different as well, right? The assumption here is if you do randomization, they'll be similar, but that's not always the case. Second, what we also look at for matching, as I was talking about, to find the control group. Now, there are various machine learning as well as statistical modeling techniques to do matching. Stratification is your standard way of looking at matching, and then you have a bunch of modeling techniques, classic distance models that we have, and then machine learning comes into the picture with propensity score modeling, genetic matching, matching frontiers, etc. So what we'll focus in this particular session is primarily on propensity scores, which was built by Donald Rubin. There's two primary major thoughts of doing matching. One is built by Donald Rubin and Paul Rosenbaum, is mostly on propensity score, and there is an alternative way of looking at which Julia Pearl has brought in, called as structural causal models. Those are slightly different, but eventually they do pretty much uh, adhere to the same sort of outcome. And there's a proof of Julia Pearl on equating both these methods. But we're going to focus mostly on propensity scores here, and we'll delve a bit into matching frontier by Gary King, but that piece is much more. We need to delve much more detail, so probably won't have time much on that. But we'll focus on propensity scores. Now, what are propensity scores? So initially there was this piece wherein we would look at a set of covariance matrix which defines a set of multidimensional of, let's say we're talking about people here, right? Multi-dimensions of people such as age, gender, education, wage, etc. And there, what we can also uh, initially there was this covariate matching method where you would compare all the x as a matrix and compare the distance of each of them uh, across the population that you have, and compare treatment and the control. But what Rosenbaum and Rubin thought that you actually, you don't need to do that, right? You possibly can bring everything down to one dimension, which is could be a single dimension, which is p of x here, which is essentially the propensity score, and bring a multidimensional vector to one single scalar. Uh, or in this case, it would eventually end up being a vector of the number of control that you have. So the second part is the treatment and control observation should be same, and the propensity score should tell you that. So how do you calculate the propensity score here? So as we were talking about, PSM is essentially collapses the vector to a scalar propensity score, and propensity score is nothing but the probability that an observation receives a treatment given the covariates. So this is sort of what Thiras was alluding to a bit, that let's say we have, these are the bunch of, let's call this green ones, probably control groups, controls, and only the yellow ones are the treatments that you know. So the job of propensity score is to find what are the corresponding pair of a control or a counterfactual for a given treatment, right? So what you do is probably use any classification algorithm. Popularly, logistic regression could use other methods as well to figure this out, right? So what you do essentially, then the third step is learn a function that matches each of them and the condition probability with respect to the X matrix and the treatment. So this eventually tells you the propensity score, right? So this tells me, for example, in this case, this guy with this has a pair of a certain propensity score. Now, eventually, after you run the logistic regression model or any classification model for that matter, what are the best matches that you get? So essentially, that's what you call uh, the propensity score here. Once that is that, so in this case, the target variable will essentially be your treatment is 1 or 0, right? So a bunch of observations. Out of that, you're trying to predict if a given observation is a treatment or not. There will be cases where the actual is actually a counterfactual, which is probably the actual value is 0, but your the probability, the predicted values will be very close to 1. So let's say 0.9 or something like that. So that tells me that even though that particular observation was a counterfactual, um, it is very similar to one particular treatment group, right? So that could be a potential match with a treatment group here, a treatment observation here. And then essentially the distance between both of those essentially gives your estimates of the lift. So that's essentially how matching helps you to actually do circumvent the need to do a randomized control trial and actually split the group between treatment and control. And there are issues like Dheeraj was mentioning about ethics, cost, so on and so forth, right? Matching frontier is another new algorithm by Gary King. I've mentioned the paper here, but very quickly on this, what this essentially does is, so one thing we can understand, one of the challenges that we have in this method is one that there needs to be some pruning, right? So if let's say I have 100 observations, out of that 5 are treated, 95 are control, I can't possibly have good matches every time, right? For all the possible observation, I can't possibly have the very good matches. So that is one. The second is, are the matches good enough? Are the propensity scores good enough? So there is a sense of balance that needs to come in. Here, balance means how good the matches are. Second, in terms of pruning, what we mean is if the matches are not good, if the scores are not good, you have to get rid of those observations, right? They're of essentially no use to you. Now, what the problem that happens there is essentially a bias variance trade-off that comes in. Why? Because if my balance is not good, my estimations won't be good. So there is a high bias problem there itself. And if my balance is good, thereby it prunes my data much more. That tends, there's a high variance problem as well, because if my data becomes too small, you can't probably trust the estimates well as well, right? So this algorithm, what it does is it sort of tries to bring a balance between the two. And I'll quickly go through this, is that if you have all the possible observations here, for example, and I've given you can probably go through this article once and get much more detail about it, and there's a paper by Gary King on this. So what this does is it calculates a Panovich distance between, you could use a different metric as well, between each of these observation and their corresponding treatment or control group. And then what you'll have is, you have to calculate the high minimum distance, and if the high minimum distance is not very high enough, is very high, then you start dropping those. So for example, in this case, 1, 4, 6 and 7 are probably very high enough. It's pretty big, right? The distance, so the size of the circle tells you how far away they are, corresponding to one of the variables that one of the observations that there are, that we are trying to match. Now, if you're dropping this essentially, and then you repeat this process one after the other, based on certain conditions, such as you could put a threshold or optimize something for it, and then you'll end up having a overall value of a treatment effect that considers both pruning as well as the balance that I was talking about. Now, regression continuity design. Now, RDD is one of the interesting challenges that you usually face in causal inference is, so let's talk it through an example. So, for example, here we have to evaluate financial aid, um, prevent dropouts in Italian colleges or any colleges for that matter. But does financial aid help in removing the dropouts? Now, the challenge here is students who receive financial aid um, and who do not are probably not, I mean, they are probably different in observed and unobserved ways. What that means is, so for example, if you look at this sort of line, it tells me that, hey, this may be the point in time where the financial aid was given, and then folks here and folks here are inherently very different because of certain variable, certain impact that was brought in. Now, what does that mean? Now, so for example, if there is a criteria that your family wealth have to be on a certain, you know, certain, so for example, your family wealth depends solely on whether financial aid depends solely on whether your family wealth is below or above a certain threshold. So for example, if this is my family wealth, if I'm if the family wealth is certain that my financial aid, I don't require financial aid, then I might fall here. And if my family wealth is above a certain threshold, let's assume it is some form of index, then my financial aid has to fall here, right? So does that inherently make these two populations comparable? Probably not, right? So what do we do there? So what we look for is something, so family wealth then becomes a running variable, right? So what we do, so the main idea is arguably students whose family wealth are just above and just below the threshold are comparable in their background. So for example, if this is my forcing variable or the running variable here, and this is where the family wealth uh, comes in terms of the threshold, we are probably going to look around only somewhere around here. So this could be my cutoff or threshold, and I can have an optimal bandwidth here, and I can probably look at only the folks here. They might be very similar, and we can probably compare them. So this is called the artificial threshold set by and by this administration, and this is what we called a local randomization. This helps us. This are the two people probably we can compare. Now, what are the advantages and disadvantages? Advantages we are fairly clear, right? Because it sort of makes it easy for us to compare to set of samples. Disadvantages, I'd say that non-linear relationships, right? If there is a non-linear relationship between the running variable and the financial aid, this could possibly be mistaken and seen as discontinuity, while it actually probably is not the case, right? And there could be contamination by other treatments, probably some other factors that actually impacts other than family wealth that we probably don't know and are unobserved that actually impacts this. Now, difference in difference is interesting in the sense that we have always worked on fixed effects regressions before. It's fairly well established. So what does difference in difference bring in the space of causal inferences? The following, right? So for example, again, we take an example here. So study is effect of increase in minimum wage on employment. So what is the goal here? If you increase the minimum wage here, and does that sort of increase the employment rate? So where are we looking at? What are our units? Fast food restaurants across New Jersey and probably eastern Pennsylvania. Now intervention, raise the state minimum wage. New Jersey raised it, but Pennsylvania probably didn't. And the outcome is the number of FT, which is the full-time employee per restaurant, observed in both these areas, both right before and after this change. What is this change? The change is this intervention, bringing the state of the minimum wage. Now there is, so the main idea here are the restaurants probably near the state border. So let's assume that Pennsylvania and New Jersey are probably nearby, but the restaurants which are in the state border are probably comparable. This is again something similar we talked about in RDD, and variations created by discontinuity in time and policy changes and space. So there could be variations because of time and space. Now these two we have considered in the RDD aspect of things. Now here, for example, if we say that there was an intervention brought in and there was a drop, for example, in the full-time employment after the or rise for that matter, there was a change in the full-time employment after the financial year. Uh, Sorry, my bad. Yeah. So there was a rise in full-time employment after the minimum wage was increased. Uh, do we see that change across the board? That change could be for other reasons as well. So how do we counter that in a way? One is we look at the control group and we actually see that change in the same time. We bring sort of a parallel trend here. So the control group, if it has have a similar change, and does the test group have a similar change? And the difference between the two essentially brings our the treatment effect. This is usually done by fixed effects regression, where probably the units here could be in the fixed effects regression. We could probably take treatment and control as the unit. Uh, Before this, we can probably go through a bit of tutorial in the sense we'll go through what uh, we look at in terms of a hands-on exercise. Okay, so I'll go through something very quickly in terms of this is a tutorial. Essentially, the code is based by a person called Konstantinos Papadopoulos. So this interestingly takes the Titanic data set and tries to find what is the effect of essentially a particular variable here, which is the treatment, on somebody surviving in or not, right? So we have a bunch of variables here. I'll just probably take this here. So we have a bunch of variables here, such as sex, age, etc. And then we what we look at are 2 to 3 different things. One, the one of the most important part here is, let me just, yeah, so we're going to talk about matching here. So in matching, for example, here we have the propensity score and the log, and two ways to look at is the propensity score and the log of the propensity score. And here, before the matching happens, we see that, for example, let's say this is the treatment, this is 0 and 1, and then here we have the treatment to be this orange line essentially, and this is across the propensity score, right? So here we see that the closer to 1 you get, you essentially have a higher treatment in terms of density, and the closer to 0 you have, essentially you have a very high uh, control, right? So treatment 0 is essentially a control or counterfactual. Something similar we see in the logic of the propensity score as well. Then I'll probably skip here because there's a few things here. For example, calculate the distance between each of the observations. Now, how do we see after matching? So if we see for example, age and fair are the two aspect of it. So for example, if we compare these two, age after density, this is before matching. So we see there's a big difference between the control and the test here, which is treatment and non-treatment. But after we do the matching, we see they're very similar. So this is the whole point of actually doing the matching here. And then similar example we see based on fair. So for example, for fair, we see there was a huge imbalance between these two, before we actually do the matching. So after doing the matching exercise, the density after the matching is something like this. So we are very close by, right? We do see both of them to be pretty close by in terms of how the observations are. So this is primarily the role of matching here. And eventually what we look at is we look at various variables and how matching impacts. But the whole point of this was to show how it will look like once the matching is done. So this is primarily from a matching standpoint. And if we move to, I have one short little code rundown for RDD. Now, RDD, as we were talking about, that RDD has a sort of library inbuilt called essentially RDD by the same folks who, and this is the project for the RDD, the Pi project. So it has two things. It has the optimal bandwidth, which finds those optimal bandwidth between the threshold that we were talking about. Let me just bring in this real quick. So for RDD, okay, this is not working. I'll go back to the code then. There are two function, which is finding the optimal bandwidth and the threshold. And this is, for example, here, if you look at the data. So this is where we were talking about that family wealth, and this is where the idea of this particular function, which is the RDD function, and finding the optimal bandwidth comes here. So how do we restrict the data around this particular threshold, right? So this uses there's a paper around that. So the way they use here, we find the optimal threshold here, which is in this particular example is 5.54, and then here essentially you look at this and truncate the data and to compare only here, and then it's pretty straightforward. Then you look at OLS model and then find the impact of each of this, right? So within this particular data point. So this primarily is a very high level view of how the RDD and matching would work. And then after this, I think Shomdeep will take us through uh, the causal ML side of things. Mm.
Hello. Thanks, Shomajit. So, in the next few minutes, we'll be walking you through causal machine learning, which is essentially on how to build prescriptive ML models using the causal concepts. So, let's take a look at this example, right? So, suppose we are providing an ad campaign to certain customers and we want to measure the impact of that on the purchase decisions, right? And we consider maybe a sample of 100,000 customers, and randomly 50,000 of them are given the treatment and the rest 50,000 are not. So now how do we understand the impact, right? So let's take the first example. So maybe 5,000 customers in the treatment group purchased the item versus 2,000 in the control who purchased it. So in this case, we can easily conclude that the treatment is super successful, and we can actually give this uh, uh, ad campaign to all of the customers and expect a huge uplift in sales, right? However, such is not the case in reality. We might see more subtle differences, like maybe 5,000 customers purchased in the treatment group, whereas 4,900 in the control group, right? So in this scenario, it's very difficult to conclude on the effectiveness of this campaign. And also we do not know which customers to target, right? So there's also a huge missed opportunity cost in this control group of 50,000, because if they would have been treated, it would have led to more significant sales. So now why can this happen, right? So it can either be the case that the treatment didn't have any effect. So the customers would have purchased it irrespective of the offer, or they would not have purchased it even if the offer was given, right? But what we might be missing out is that maybe a small group of customers have purchased the item after getting the offer who would not have otherwise, and the other group of customers may have purchased it without the offer. So these effects are getting cancelled out. So now how does one go about understanding whom to give that optimal treatment, right? So that is where causal machine learning comes into play. So how is it different from the traditional predictive machine learning, right? So in both of them we have like the input variables x and the outcome y, but in addition here we have a controllable and known treatment, which is the t, right? And usually in most of the cases in the predictive ML models, our goal is to estimate the expectation of y given x. But here we want to measure the causal relationship, which is given by expectation of y given x and t. And the main difference is in the predictive ML, it's a very passive approach. So we can predict the actual effect or the actual outcome, but we do not have any control over it. We cannot change it. But here we can actually effectively impact the outcome by properly identifying the treatment and applying it in such places where the impact would be maximized. So for example, like instead of predicting the sales based on some past data, we can also effectively optimize it by changing some of the controllable factors like the price, the discounts, inventory, and other things. And also another point is the difference between the causal ML and the causal inference. So the causal inference, what we just discussed, was more around understanding the impact of any treatment, whether it's positive, negative, neutral, and so on. Whereas in the causal ML, we are going to personalize the treatment. We want to understand which observational units it needs to be applied to so that the response is best. So let's take a look at the effect of the treatment on the individual customers, right? So the first case, right, where the customer is given the treatment and they purchase the item after that, and without the offer they are not purchasing. So these type of customers are called persuadable. So we have effectively persuaded the customer to purchase the item with the offer. Now the other cases are like where the customers would purchase the item irrespective of the offer, so they are sure things. Then there are cases where the customers would not purchase irrespective of the offer, so these are like lost causes, we cannot do anything about them. And then there are others, the more dangerous category, who might have purchased otherwise but will not do during an offer. So these are like the sleeping dogs, we definitely don't want to target them. So here if we see, like, these are the different impacts of the individual treatment effects. And when we take an average here, so that is the average treatment effect of the expectation of the outcome during treatment and without the treatment. So now this is very important for the causal inference, but here we really want to understand whom to treat, right? So that is where we go to the conditional average treatment effect. So here, other than the treatment and the outcome, we have other independent covariates which might affect the purchase decision, right? So and in this case, we can again take the conditional expectation of y minus y1 minus y0 given the independent variables x. And because the effects really differ across the different segments of the customers, we cannot easily calculate this Kate value. So now let's take an example, right? Maybe a deeper dive into the example of the campaign that we are talking about. So suppose the offer is like this: you purchase two private brand diapers and get one for free, right? So now the effect on all the customers is obviously just y given treatment minus y given the without the treatment. Now, of course, this might change a lot if the customer is married, and again, if there are two children, then the impact will change, right? Then like if the customers are price conscious, then there'll be a different effect. Whereas if they are brand conscious, if they want to choose to their favorite brands, it might have a different effect. So this different effects in the different group of customers is called the heterogeneous treatment effect. And so as these number of covariates keep on increasing, we cannot simply take the difference of these averages, these conditional averages, to measure the Kate, and it brings us to more sophisticated ML techniques. So that is where we go to the uplift models, which are essentially ML models for to estimate the Kate from the observational data, and we can conceptually present the customer base into this form of a tree-based structure. And our goal would be to go from this entire customer base to the perceivable, so that we can effectively target them. Right. So now there are a lot of different techniques of how we can achieve this. So broadly, two classes: one are the meta learner approaches, and then the direct uplift estimation. So in the meta learner, again, multiple different approaches. There are transformed outcome, single model, two model approaches, and the WD biased ML. And then in the direct uplift, again, we have tree based approaches, instrumental variables, and deep learning based techniques. So starting off with the transformed outcome approach, right? So here, what we are effectively doing is we are changing the outcome based on what treatment was given, right? So if the treatment was 1 and then the outcome was 1, we are making the transformed outcome as 2. If the treatment was 0, so it's in a control group and they purchase the item, then we are making it -2. In all the other cases, it is 0. So this can be written as this transformation, like the new transform variable zi will be 2 into yi ti minus 2 yi into 1 minus ti. Now it can be shown that this the expectation of this transform variable z given x comes out to be the same as the Kate value. So which is essentially we are finding an unbiased estimator of the Kate through this transform variable, of course under certain appropriate assumptions. So for example, we are assuming that the treatment is randomly applied, as well as there's an equal proportion of treatment and control. Now that may not always hold true. So if it doesn't, then how can we generalize this? So that is where propensity score based techniques again come into play. So we can actually create another transformation using the function of the treatment and the propensity score. And here, if we keep uh, applying certain assumptions, like maybe if they are randomly distributed but with unequal probability p, we can just substitute the propensity score with that unequal p, and then if that also becomes equal, then it boils down to the same equation that we talked about before. Now once we have done with these transformations, then we can apply any supervised ML regression problem, say an XGBoost or any kind of gradient boosting models to solve for this. Right now, the advantage is here, right? It's a very simple transformation followed by any of the known ML models, right? And it really works well for the large data sets, and also for the binary treatment where it's a 0-1 kind of a situation. Now the disadvantage is here, there can be a high variance in the estimate, especially if we are having a small or medium sized data. And this is not suitable for continuous or multi-level discrete treatment. So what do we really mean by the continuous treatment, right? So far by treatment, we were talking about some offer, it's a binary, we are either giving it to someone or not, right? But continuous treatment can be something like this. So consider a store is selling some fresh baked goods like breads or cakes and so on. And if we are not able to sell that within a stipulated amount of time, it goes to waste. So in such scenario, what we can do is we can provide dynamic discounts so that we are able to sell that product in time, right? So in that scenario, the discount itself become the treatment. So here we are defining the Kate value as the differential of the outcome given the treatment, and then we take the conditional expectation of that with respect to the known variables x, right? So in this scenario also um, we can take the transformed outcome as just a function of the treatment, and then in case it so happens that it's not a not randomized treatment allocation, we can actually build another model which predicts the treatment on the known variables x, and then we can use that as the transformation. So effectively we have shown how to generalize the transformed outcome even for the continuous treatment. Now we'll quickly go through some of the other meta-learner techniques. So single model, right? The S-learner is a very simple baseline model where we are using the simple model and we are using treatment as another feature, and we just substitute the values and find the difference to estimate the gate. While it's a very simple model and it works well for both discrete and the continuous treatments, the disadvantages are that it can often bias the treatment effect towards zero, especially if we are using regularization, and also the model can learn to ignore the treatment effect if there are other more influential covariates present. So we can overcome this using the two model approach, the T-learner approaches. So here we have essentially two models, either completely independent or with some conditional dependence, and where so essentially one model is for the treatment, another for the control, and then we use the difference of the predictions of these two models to get the Kate value. Now, here comes the problem, right? So in many cases, there can be a very small treatment size compared to the control. So in such scenario, the treatment model has to be simple, otherwise it will overfit. And the control model with its larger size, it needs to be more complex than the treatment model. So in this example, the Kate effect is very linear or constant, but because of the way the data is distributed, it leads to a spurious treatment effect, which is a nonlinear in this case, right? So now, um, again, like the advantages are definitely easy to implement ML models, and like we overcome the problem of the S learner in terms of missing out the effect, but then this can suffer from the regularization bias, especially if the treatment effect is small, and it still doesn't work for the continuous treatment, right? So we can overcome this by using the X learner, which essentially starts off with using the T learner as the first step, and at the second step we are imputing the treatment effects from the other part of the data, and at the third stage we build another model on the other part of the data on which it was not initially trained to get these effects, and then finally we take an aggregate using the propensity score. So it definitely overcomes the problems of the S learner and the T learner, but like it's also significantly more complicated, and it still doesn't generalize to the continuous treatments. So now we take a look at like a model which works for the continuous treatment. So here we have the double debiased ML models. So what we taking a look back at the example of the fresh products, right? So in those scenario, there can be variables which can affect both the treatment and as well as the outcome, right? For example, the day of the week, the time of the day, or the temperature, and so on. So we need to remove the effect of these confounding variables from both the treatment and the outcome. So we can do this using this double debiased ML. So in this case, we have two models. One is to denoise the outcome and another to debias the treatment effect. So once we have got the residual from these debiased and denoised parts, then we finally have another regression model on this to estimate the effect of the gate. Now it's a very generalized framework which works very well for the continuous and the discrete cases. However, there can still be overfitting because of the multi-stage models, and the other part is it really doesn't work for the non-linear relationship, so we might need to linearize them beforehand. So we'll quickly go through some of the other parts. So one is related to the direct uplift estimation, right? So here the most important one I would say is the tree-based approach, right? So here we can actually represent the data in this format where uh, so it's a form of the classification tree, but the difference from a traditional classification tree is instead of focusing on splitting the tree based on the loss function around the outcome, here we are more focused on the treatment effect. So we are effectively splitting the tree in such a way that the distributional divergence between these two nodes are maximized, and we can do this using multiple different methods. We can use a KL divergence method or Euclidean distance. And so the advantage is definitely it's a very simple way of using the known framework of tree-based models and effectively maximizing for the treatment effect. Disadvantages, so there can be some cases where maybe the number of nodes are growing very rapidly. So in those cases, we might have to apply certain penalty on it, or there can be even cases when it is the the distribution of the treatment and control is not matching. So in those cases, we can apply additional penalty using the Gini impurity. So next, like we talked about the instrumental variables in some time back. Now we can also use such instrumental variables to measure the effect of the gate. So there are two broad approaches here. One is using a two-stage least square technique, where we first have uh, a regression model of the treatment on these instrumental variables, and then once we get the fitted treatment value, then we have a regression of the outcome on this fitted treatment value. The other case is using a doubly robust instrumental variable, again a two-stage technique, one from getting the outcome from the treatment, the control, and then the treatment from the controls. So again, very this works well in case there are like lot of confounders present, and there are variables which are affecting both the treatment and the control. But so this can take care of the omitted variable bias, and uh, the difficulty here is, like, if the instrumental variable is not properly chosen, it can be a weak first stage learner, and the relationship with the treatment may not be very good. And also these instrumental variables also introduce bias. So if there are a lot of instruments which are used, then it can eventually lead to more bias in the outcome. So next we will cover, like, briefly some of the deep learning techniques. There are broadly two which are available at this point. So one is using the causal effect variational autoencoder. So the VAEs in general learn the distribution of the features in the latent space. Here we are learning the causal relationship, the causal underlying causal structure among these relations, like this is the treatment, and how it affects the outcome and what are the confounding variables. So here there are two approaches, like one on the inference network, another the model network. So, and even between those, there are options to switch between the network depending on the treatment value. And the other part is related to DragonNet, which is a 3-layer neural network. So there are two um, deep neural networks, one for the one for the outcome, one based on the treatment, another based on the control, and then another third map, which is it's a simple map followed by a sigmoid for the propensity score. So now these methods also work well in terms of understanding the underlying causal structure. And usually what we have seen is in the presence of like noise, these methods work really well. But in case there are not a lot of noise present in the data, then like some of the more traditional techniques work better. And also this is useful in terms of the variable selection, and it can take care of cases where there are some variables which may not be important for the conditional effects. So next, going to understand like how do we measure the goodness of fit of these uplift models, right? So the traditional MSC type methods do not work because the ground truth of the Kate is actually never known. So in such scenario, we can have multiple different techniques. One is called the uplift decile plot. So what we are doing here is we are grouping the predicted uplift values into deciles, and then at each such decile group we are plotting the actual uplift value aggregated at that level. So so in this case, like a monotonically decreasing curve across the as we move along the deciles would show the directional correctness of these models. But on to more quantitative measures, right? So taking a cue from the ROC curve, from the traditional um, machine learning techniques, classification techniques. So what we have here is an uplift curve or a Kinney curve. So essentially here we are plotting the fraction of data that is targeted, and according to that, at that point, what is the uplift value. So which is the difference of the positive outcome in the treatment minus the positive outcome in the control. So that is what we are plotting here, and the blue line is the outcome of the model that we have fitted. And then there are a couple of other lines, right? So one is on the random selection. So if we would have randomly selected the treatment effect, what how it would vary. And then there are theoretical maximums and the practical maximums, depending on, like, suppose if only the only the cases where there is a direct uplift expected from those getting the treatment, only those are converting. That is like the theoretical maximum, and then we have dependence on the sleeping dogs and so on. So from there we can actually measure the area under the curve between this, the predicted by the model, the blue line, and the one which is by the random selection. So this is the area under the curve that we are looking at. And that, if we normalize by the area under the practical maximum, so that gives us a quantifiable measure of the goodness of fit of this uplift model. And we can actually have certain alternative techniques using cumulative curves and so on. Now, going back to the initial example, right? Like, how can we use these uplift concepts to actually have a strategy of targeting the customers effectively, right? So here, for example, at the very first stage, if we don't have anything done, so we can have a first stage of campaign using the affinity of the customers towards that product, and then we use that data, like on a smaller subset of customers, we understand who converted and who didn't. From there we can build the uplift models, and then at the second stage we can have maybe a larger group of customers where we are using both uplift and affinity to select these groups of customers. And we can actually use a two-way factorial ANOVA model to measure the effects of these uplift and the affinity and their interaction together. So whether both of them should be considered in creating and personalizing the treatment, or maybe one of them is more significant than the other. So because of the similar distribution, we can actually do a direct comparison. And so this is an example where we are showing, like at this group of the affinity and uplift combinations, we are applying the treatment and the control, and from there how can we measure what is the treatment effect and what is the interaction between the treatment and the affinity based selection, and which group, which selection is more significant than the others. So with that, we'll pass on to Dheeraj to show a practical demonstration of these causal ML models.
Thanks, Somdeep. I'll take you through hands-on exercise to work with causal ML models. Yeah, we shall go through a few meta-learners, which Somdeep had taken you through, namely transformed outcome, S-learner, T-learner, and X-learner. So the data set that we would use is an email campaign data, where customers of an investment firm are sent emails asking them to subscribe for their products. So it has the below features, named age, income, the invested amount, the email, which is a binary variable. If an email is sent to a customer, it is 1, otherwise 0, and whether the customer converted or not by subscribing to that email. So 1 is if the customer had subscribed, and 0 otherwise. So we import the necessary libraries. And the data is taken from this source. So this is a causal inference book. It's called the Causal Inference for the Brave and True. So it's a good book to get started with causal inference. The resource is kept here. So we read the data, then split the data into train and test. Hope this is visible to everyone. Then we assign labels, converted, which is the outcome, the email, which is the treatment, and the confounders, age, income, insurance, and invested, which are the x's. X is the confounders. So to do the transformed outcome way of estimating the causal effect, so first we would transform the outcome y. So y is the outcome which is converted 1 or 0, and we multiply that with the factor treatment minus propensity score over propensity score into 1 minus propensity score. So this would be our transformed outcome, and we would take an expectation of y star, the transformed outcome, which would give us the Kate. So propensity score, so the data is randomized here, so the propensity score would be nothing but the mean of the treatment. Since it's 1 and 0, so we can directly compute the mean, and we would transform the outcome here, y star. And so we can fit in any off-the-shelf machine learning models. We can take an LGBM regressor and pass in the parameters, desired parameters. So we fit the training data and pass in the transformed y here, and we can estimate the Kate. We can predict it over the test set, and so these are the results. So how to interpret them? So the result is 0.10 for the customer 6958. So how do we interpret this? So a customer having an age of 40.9 and income 4486, insurance and invested amount so much. So if we do send the customer an email, so the probability that the customer would subscribe to the product would increase by 10%. So, and similarly, so this is 0.04. So if we send an email to the customer having these characteristics, the probability that the customer would subscribe to the product would increase by 4.6%. And we can evaluate the goodness of it or how well our model is performing against random. So this is the cumulative gain curve that Somdeep had also talked about. So our causal ML model, which is the transformed outcome in light blue color. So the larger the area under the curve, the better our model is performing. So here it is 0.6 against 0.5 of random. And we will now look at S-learner. S-learner is a simple method of estimating the causal effect. So in S-learner, we would fit a single model. That's why the name S-learner. So it's uh, pretty straightforward, as in, so we would also use the treatment as a predictor for the outcome. So along with X, we would also use the treatment T to predict the outcome Y. So we use, so this is what is mentioned in the picture. So we have X and T. So we are building a model in the training phase. In the prediction phase, to estimate the causal effect, the treatment effect, so we input treatment is equal to 0 for the data set and compute the outcome, and treatment is equal to 1 and compute the outcome. Take a difference and estimate the gate. So we use the library, the Causal ML library. So this is developed by Uber. Uh, Pretty interesting and powerful library. So we have this regressor called the base S regressor. So we would initialize the regressor by passing in any of the regressors, sklearn regressors or XGBoost. So we use the XGBoost regressor here, and we can estimate the average treatment effect by calling the estimate underscore AT method. So we pass the X, the treatment, and Y, and it returns the treatment effect. So if we were to give treatment to all the population, so the effect would be 0.63. So the probability that uh, they would subscribe would be 0.63. Yeah. Now we can fit the training data on the S-learner that we have initialized and estimate the gate on the test data and plot the gain curve again and see how the learner is performing. So compared to random, it's more or less same compared to the random. So it's the area under the curve, under the uplift curve, is 0.52 compared to 0.5 of random. So one disadvantage with S-learner is that, so if the treatment is weak or if other covariates have stronger influence, the effect of treatment would be diminished, and so it has a tendency to predict zeros for the effect. So T-learner overcomes this challenge by fitting in two models. So that's where the name T comes from. So it fits two models, one for each of the subpopulation of treatment level. For treatment level 0, that is for the data set without treatment, it fits a model. And for data set with treatment is equal to 1, it fits another model. And the estimated K8 is nothing but the difference in the predictions of these models when the predictions are done on these two separate data sets. So we import the base T regressor from the same library, Causal ML, and we can pass in any of the regressors. So we use the same XGBoost, and we can estimate the average treatment effect. So this is 0.068, and we follow the same procedure. So we fit on the training data, passing the outcome on the treatment. So internally, what it does is it fits two models, one for each treatment level, t is equal to 0 and 1. And while prediction, so it does two predictions and returns the gate. So we can plot the gain curve here as well. So compared to the S learner, it is doing a better job in estimating the gate. So the results would be 0.58 for our T learner. So, but when the data set sizes are very different, when we have very few treatment observations, so this might create a problem, and it might not learn the non-linearities in the control set, which is most of the times larger. So we have XLearner, which overcomes this difficulty. So the calculations are more involved here. So the first stage is same as the T-learner, and in the second stage it fits the treatment effects in the other data sets, and the results from there is used and weighted with the propensity scores to estimate the gate. The process that we follow is similar. So we call the base regressor here. For the X learner, it is the base X regressor. We pass in the XGBoost regressor, the estimate the average treatment effect, fit on the training data, and estimate the gate. So we evaluate it with the gain curve and observe that the area under curve is 0.54. So all these learners essentially work different on different data sets, like all machine learning models. So which learner works best with which data is quite subjective. In our data sets, it is quite randomized. So we see that a transformed outcome seems to outperform the other learners. So it all depends on the kind of data set and how the treatment and control observations are present in the data. So this is for the hands-on, and we would like to mention an alternate framework just as mentioned. So this is called the structural causal models. This by Julia Pearl. It's an alternative framework to the potential outcome framework that is typically used. And these are some resources, some libraries and books, articles. So Causal ML is the one that we use, developed by Uber. Econ ML is by Microsoft. Econ ML and DoY, they're quite powerful in working with Causal ML. So both of them together, DoY and Econ ML, are uh, quite powerful when used together. And we have PyLift and Keyway, and some of the books and articles that were referred to here. Yeah. So that's mostly it from our side. So would be happy to take any questions if there are any. Yeah. We can close if there are no questions. Thank you. Thank you.
I thank the speakers for a very nice session. Are you sure there are no questions? We still have time. Um, okay. Yeah, I can ask some questions. I was trying to understand the matching framework. Okay, there is a question in chat. Let's take that first. The question is, causal model different from explainable AI? How are the causal models different from explainable AI models?
Um, Explainable AI, like stuff like shapely values and a few other things, they spend a lot of time explaining the impact of the variables which can be the machine learning models. So in causal, the it's essentially causality that we're looking at, why something is happening. As against explainable AI, mostly, I mean, there are similarities, there are overlaps, but what it talks, explainable AI, such as shapely values, mostly probably talks about the impact of certain contribution of certain weights, or certain factors or certain variables in the overall um, target variable, so to say. So doesn't necessarily have to be causation all the time. But yeah, I mean, there are overlaps. There are sort of similar, but the difference would be focus mostly on causation and causal model, I would say. But I don't know. Shamdi, do you want to add something?
Yeah, it's mainly that. I mean, the explainable AI part is mostly post hoc, right? After we have built a model, then we are trying to explain it with the features that we have, and it's still based on the correlation framework. Whereas largely in causal, we are trying to kind of understand whether like these features really caused the other and so on. So that is like the fundamental difference. And here we can explicitly measure the effect, as well as we can have the causal ML models, which where we can change the treatment variables and change the outcome, which we are not able to do that in the explainable AI. It's just we are just trying to explain like why this outcome happened and so on. So
Thank you. Um, where can we find these slides?
We'll be sharing that, and also the GitHub link as well.
So the slides and the notebooks will be shared. Okay, that's it. Okay, I have a question. You explained propensity score matching and matching methods, which I understand is that, let's say you have the real treatment, like pill equal to 1, and but you don't know for the same subject what is pill equal to 0. So let's find a nearest match which can serve as the counterfactual, right? So how do you, means in what space are you finding that match?
We have a set of covariates, right? So we would match on that set of covariates. In our example, in the most recent example, we could match on the age and the income and the invested amount of the customer. So yeah, want to add anything?
Yeah, I mean, essentially, we could use. We have the covariates in place, right? And then a target variable will essentially be treatment, 1 or 0, for a given set of covariates. Then essentially that's where. So you're trying to predict if a given observation is a treatment or not. You actually know what's a treatment and what's not a treatment, so to say. Then the cases where it's actually not a treatment, are those propensity scores high? So that means they could possibly be very similar to a treatment. So we can probably close them something similar to a match there. Yeah.
Thank you very much. Any further questions? Okay, if no questions, then we can give a round of applause to the speakers. Thank you very much. Now we can